So this problem is really all about the setup and whether you're accounting for all the gases properly. And sometimes it helps to draw a small picture. So we have a container where oxygen gas is being collected, but it's over water. And anytime something's collected over water, so there's a couple things going on. We've got the oxygen gas in there, but we also have this contamination because some of this water is vaporizing into water vapor. And so anything told to us about this must include the water. So there's really several things that we can be keeping track of here. Inside this container, we can keep track of the oxygen, we can keep track of the water, and it also helps to have a column about the total. What do we know? And so we want to write down the pressure, volume, temperature, and moles. Pressure, volume, these are the variables which we can assign to each of these things. So let's look and start. What do we know? It's collected over water at 65 degrees Celsius. So that means that the oxygen is at 65 degrees Celsius. It means the water is at 65 degrees Celsius. And the entire container is at 65 degrees Celsius. And the pressure is at 2.3 atmospheres. Here's where we have to be careful. The total pressure is at 2.3 atmospheres, not just the oxygen or the water. We need to include them both. So we have that information there. Now, what else do we know right now? Well, we know something else about the oxygen that's going to be collected and put into a new container. So this oxygen here is going to be separated from the water and placed into a new container. And this particular oxygen, same oxygen, just new container, but we can make a new set for it, has its own pressure, volume, temperature, and moles. And according to this, its volume is 6.8 liters at STP. That's 1 atmosphere and 0 degrees Celsius. So we know that, we don't know the moles of that. So that's everything we know about this problem is given in the problem statement. And we're ultimately looking for the volume of oxygen initially collected, this value here. And so we have to figure out how to get there somehow. So as it stands, there's not currently enough information to solve the problem. We need more. And one thing we can do is there's a few ways to go about this, but one thing I want to do is anytime something's collected over water, we know the pressure of the water because we know the temperature of the water. What we can do is consult our water vapor pressure chart. So if I consult my water vapor pressure chart, at 65 degrees, the pressure of the water is 0.2467 atmospheres. So I'm going to write 0.2467 atmospheres. That is the pressure of the water vapor at this temperature. And that's entirely dependent on the temperature, nothing else. I know that for a fact. So knowing that, I know the pressure of the oxygen in the original system. It's just a matter of subtracting the pressure of the water from the total. So if I take my 2.3 atmospheres minus 0.2467, I get 2.0533 atmospheres. But that's still not quite enough to solve this. I'm looking for V. And there's two ways to go about this problem at this point. One is, normally if I'm looking for V, I can use the equation PV equals nRT and solve for V. But I don't know my moles. So I can't use this equation unless I know my moles. So one way to go about doing this problem is to find the moles of oxygen using this equation. Because PV equals nRT, I can solve for the moles of the oxygen in this situation, which is really the same gas. So if I do that, P, by the way, remember, I'm always using Kelvin. So this is 273 Kelvin, and then 65 plus 273, it's going to be 338 Kelvin. Don't want to get into the mistake of using Celsius. So if I solve for moles there, I can do P, so 1 times 6.8 divided by 0.0821 divided by 273. I get 0.303 moles. So this is one way to do it. And then I can take this and plug it in up here because it's the same gas, so it's the same number of moles. And then I've got P, T, and N I can solve for V. So that is one way to approach the problem. And I could do that, but I'll let you handle it if you want to do it that way. That requires two equations. I have to use the PV-nRT equation twice. The other way I can do it is I can say, hey, I know P, T, and I'm looking for V for this gas, and I know PV and T for this gas. They're the same gases. So I can say P1 V1 over T1 equals P2 V2 over T2. Only for the oxygen. I am completely ignoring the water and the total because these are not referring to the oxygen gas. I only care about how these two are related. So I'm looking for, let's call this P1 V1 T1. Let's call this P2 V2 T2. It doesn't really matter. So I'm solving for V1. So if I do this algebraically, V1 is going to equal P2 V2 times T1 over P1 times T2. And that's what I'm going to do. I'm going to plug in. So if I plug these numbers in, and I'll just kind of do this on my calculator. Trust you can handle this yourselves. 1 times 6.8 times 338 divided by P1, which is 2.0533, divided by 273 Kelvin. I get a volume of 4.1 liters. And incidentally, that's the same answer you'll get if you use the PV equals nRT to solve for V here. So again, two methods to solve this problem. It really doesn't matter, but notice the organization was key to solving this. Writing down each of the gases in the total in the original, and then this is the oxygen in the new container. I have to really account for this information. So until next time, I am Derek Genova. Have a delightful day.